Raw audio is honestly a complete and total mess. It's just this chaotic jumble of overlapping frequencies, random background noise, and wildly varying vocal pitches. But if you're trying to ace an audio machine learning interview, you've got to prove that you can take all that chaos and extract clean, speaker-independent phonetic features. And the way you do that, you master the MFCC pipeline.
So, it really comes down to one fundamental question. How do computers actually hear? See, they don't care about the physical sound waves floating through the air like our ears do. They need a purely mathematical representation, something that separates the meaningful parts of speech, the actual words we're trying to say, from both the raw acoustic data and the unique pitch of the specific person saying them. That's the ultimate challenge we're unpacking in today's explainer.
Here's our agenda. 1. The source filter model. 2. Building the MFCC pipeline. 3. Warping the Mel scale. 4. DCT and pitch removal. 5. Modern ASR versus MFCC. And 6. The 60-second whiteboard.
Section 1. The source filter model, separating pitch from meaning.
Okay, before we even touch the math, we need to think about this whole process like an acoustic guitar. It's a perfect analogy. The source is the guitar string. In human terms, that's your vocal cords vibrating to create a bass pitch, or F0. Now, the filter is the actual body of the guitar, which is like your vocal tract, your throat, tongue, and lips. If you play the exact same string on two totally different guitars, it's going to sound completely different, right? Because the body filters the sound. In speech processing, we really just want to capture that filter, because the filter is what actually gives shape to the specific word you're saying.
Let's clear up a massive interview myth right out of the gate. When we say source, we do not mean background noise. Not at all. Source specifically means vocal cord vibration. And here is a huge trap that catches so many people. Fricatives. Sounds like s or sh. Those are produced by turbulent airflow. They literally don't have a pitch. So a lot of candidates assume MFCC just removes them. Absolutely not. MFCC captures their spectral envelope perfectly because we desperately need those sounds to tell the difference between a word like sip and ship.
Section 2. Building the MFCC pipeline, the 10-step process.
This process can look incredibly intimidating, so let's just break it down into 3 digestible macro phases. First up is pre-processing, where we chop up and prep the signal. Second is frequency analysis, where we extract the spectrum and sort of mimic how human ears work. And finally, decorrelation, where we successfully isolate the speech from the pitch.
All right, you absolutely have to memorize these industry-standard numbers for the first phase. We sample at 16 kilohertz. That captures all the useful speech frequencies up to 8 kilohertz. Then, we chop the audio into little frames of 25 milliseconds, and we step forward 10 milliseconds at a time. Now, why 25 milliseconds? Well, human speech is non-stationary. It's always changing. But the math we use requires a steady, locally stationary input. 25 milliseconds happens to be the exact sweet spot where a phoneme holds relatively steady.
But here's the catch. When you arbitrarily chop a continuous wave into a 25 millisecond block, you create these sharp artificial edges at the cuts. The math we use next, the fast Fourier transform, gets totally confused by this. It interprets those sharp edges as fake high-frequency noise, which causes your real frequencies to smear and bleed all over the spectrum. It's called spectral leakage, and we absolutely have to fix it.
The fix is a windowing function. Now listen closely, because interviewers love to hit you with this gotcha question. The standard window we use is the Hamming window. It is definitely not a triangle. A Bartlett window is a triangle. The Hamming window is a very specific, smooth cosine bell designed to gently taper the frame's edges down to near zero, and it works incredibly well. Hamming suppresses that spectral leakage at negative 43 decibels. To put that into perspective, that's roughly 60 times better suppression than what you'd get from a basic triangle window.
Section 3. Warping the Mel scale, mimicking human hearing.
Okay, so after running the FFT, we're left with 257 unique frequency bands. That's a lot of data. Our goal now is dimension reduction. We're going to compress all 257 of those bins down into just 40 Mel filters.
So why do we use the Mel scale for this compression? Simple. Human hearing is logarithmic, not linear. Think about it. If you hear a jump from 100 to 200 hertz, that's a massive musical difference. But that exact same 100 hertz difference between 7,000 and 7,100 hertz, your ear barely even registers it. By placing 40 filters equally along the Mel axis, The actual result in hertz gets really dense at the low frequencies and sparse at the high ones. It's an absolutely brilliant trick because it focuses all our computational power exactly where the crucial vowel sounds live.
Stop right here, because this is literally the single biggest trap in an audio ML interview. The Mel filter bank does not remove pitch. I repeat, it does not remove pitch. It reduces dimensions, sure, and it warps frequencies to match human ears. But the raw pitch harmonics, the actual source string vibrating, are still completely mixed in with the filter at this point in the pipeline.
Section 4, DCT, and pitch removal, achieving speaker independence.
All right, this is where the real magic happens, the final 3 steps. First, we take the logarithm of the Mel filter bank energies. Second, we apply the discrete cosine transform, or DCT. And third, we truncate the results. Why do we take the log? Because doing that magically converts our source times filter mathematical model into source plus filter. And once they are added together, we can finally pull them apart.
And here's the secret to the whole pipeline. When we apply that DCT to the log spectrum, it separates the signal out by speed. The vocal tract formants, the actual shape of the words you are saying, create this very slow, smooth envelope. The DCT captures this perfectly in the low-order coefficients, numbers 0 through 12. The speaker's unique pitch, on the other hand, acts like a really fast, high-frequency ripple. The DCT pushes all of that ripple into the high-order coefficients, 13 through 39. So by simply keeping the first 13 and literally throwing the rest in the trash, we automatically discard the pitch.
After all that heavy lifting, we finally arrive at our feature vector for a single frame of audio, which is exactly 39 dimensions. We've got the 13 MFCCs we just kept, but speech is dynamic, right? It changes. So we append 13 deltas to represent the velocity of the speech over time, and 13 delta-deltas for the acceleration. So there it is, 39 numbers that perfectly describe a human phoneme, regardless of who happens to be speaking.
Section 5, Modern ASR versus MFCC. When to use what?
Now you might be wondering, with all the crazy advancements in modern deep learning, do we actually still use all 10 of these steps today? Well, the answer is a bit nuanced. Classic systems absolutely needed the full MFCC because older models just couldn't handle correlated data. But today, modern neural networks like transformers and conformers are wildly powerful. They actually prefer stopping right before the DCT step, using the 40 to 80 dimensional log Mel features. They just handle the correlation and pitch extraction internally. That being said, knowing the complete MFCC math inside and out is exactly how you prove to an interviewer that you possess a deep, fundamental understanding of audio signal processing.
Section 6, the 60-second whiteboard, your interview summary.
Okay, here's the payoff. If you're at the whiteboard, this is your 60-second summary. MFCC extracts speaker-independent phonetic features. We sample at 16 kHz, chop into 25 millisecond overlapping frames, apply a Hamming window, a smooth cosine bell to suppress leakage, take the FFT, pass through about 40 Mel filters dense at low frequencies, take the log to compress dynamic range, apply the DCT, and keep the first 13 coefficients to isolate the smooth vocal tract envelope while discarding the rapid pitch ripple. We append deltas for dynamics. Result, a 39-dimensional vector per frame. Practice that out loud. It is super dense, but you now know the logic behind every single word of it. Now, I want to leave you with one final thought. We just spent this entire explainer meticulously throwing away pitch to achieve speaker independence. But what if you were building a system for a tonal language like Mandarin, where the pitch literally changes the meaning of the word entirely? How would you redesign this pipeline to add F0 back into the mix? Think about it. I will give the drive link to download dimensions. Keep learning, and I'll catch you next time.